Alright, so in our final lesson for the snow day, and for what we're going to do today, we're going to look at kind of another examination of finding areas using definite integrals. The first thing that we're going to look at, which is really a review of what we've already done, is we're going to look at the area under the curve bounded by the given function, vertical lines, and the x-axis. The vertical lines are going to be your min and max of your interval, your a to b that are defining your function. Then we're going to switch gears just a little bit and we're going to go to area under the curve, but now we're going to be bounded by the function horizontal lines and the y-axis. So what we're basically going to be doing is, instead of finding area between the curve and the x-axis, we're going to be looking at area between the curve and the y-axis, and to figure out how that can be set up. And then we're going to finish out the lesson today with looking at the area between two curves of two given functions. All right, so let's start with the review, and let's go back to area under the curve. We're bounded by the function, vertical lines, and the x-axis. So the idea is, as kind of talking through this set of notes, is that here are the two vertical lines. You have your x equal to a, which defines your low boundary. You have your x equal to b, which defines the upper boundary or the upper limit of your definite integral. And we're trying to find the area between this positive curve and the x-axis. And since f of x is always positive in this region, then we know that the area is exactly the same as the definite integral from a to b of f of x dx. And so that was what we've been kind of working with up until this point. Typically, if you want to calculate the area, you should sketch it, because you do want to determine if you're always above or above and below, where you would have to split it and then create and make the area, the definite integral, positive in order to have area. You're going to figure out your boundaries and then set up your integral, and you're going to integrate. Now, right now, for this section, we'll come back to this, right now we're going to be using the calculator to estimate. Okay, because right now the important part of this lesson is the setup and getting the right definite integrals to represent the area, not necessarily the technique of integrating and doing it algebraically. Right? So just quick recap, going back through some examples we've done similar to these. I want to find the area in the first quadrant bounded by the function 4x minus x squared. So you can see from your picture here that essentially what you need to do is you need to know where it intersects the x-axis. Once I have this, that'll give me my a and b for the setup of my integral. Remember, we're doing the integral from a to b of f of x dx, and that is going to represent the area in this problem. And remember, the reason that we're doing it this way is because you could think of this as having a representative little rectangle. Our rectangles have delta x or dx as their width, and then the height is determined by your f of x star, okay, depending on whatever endpoint that you're doing. And remember, then we turned it into a limit, let the number of rectangles go to infinity, and that's how we ended up with our definite integral. But the important part is, by looking at this and realizing that what we're doing is we're sectioning it using vertical rectangles, where the width is the delta x or dx and the height is the function value at that x value. Right? So we find the boundaries, you find your x-intercepts, pretty straightforward, factor, zero product property, so we get 0 and 4. So this is going to give us our lower limit and our upper limit of our integration. And what we're basically going to be integrating is 0 to 4, 4x minus x squared dx. And again, we haven't learned a shortcut for this yet. So right now when I say solve in this set of notes, I just want you to use the calculator. So we'll just recap that real quick, make sure everybody's got an understanding of how the calculator works for this. Let me move this over here for myself. So we're going to be calculating, now I'm going to do it from the home screen because we're just doing a definite integral. I don't need to worry about looking at the graph and seeing the area show up, although it's certainly okay if you want to do that. You can go to your y equals, and let me just clear out what I have going here. Our function was our 4x minus x squared. And you have to work with me on my calculator. You know, I have to kind of trigger happy little buttons here. So there's my 4 minus x squared. Let's set our window. We're interested in 0 to 4. So I might do, let's do negative 2 to 2 just to see more than what we're going to have. So negative 2 to 6 maybe. And then in terms of my y window, probably going to pick something, like if I put in negative 2, I would get a negative 4. Let's try negative 10, and maybe let's go up to 50. Let's see what that's going to do for me. That's probably a little high. I can tell I have a little preview down here, so maybe let's only go up to 20. Let's try that. Yeah, I'm not even, that's good enough for what we're going to do. So I can take a look at my graph. You can kind of see it coming over here in the little thumbnail or down here. And I want to calculate my interval. So what we can do is we can go to Second Calc. We can choose number 7. We can ask it to calculate from 0 to 4. And then it will calculate that for us. And I get 10.6667. And let's just verify that is the 32/3 that I have written as my answer that's there. Now the second way that you can do this problem is we can use the math menu, and I can do it right here on the home screen. So I can go to the math menu and notice that number 9 is function int, which is the function integral. So I'm going to choose number 9, and if you have the new calculator like I do, let me get back over here, then it'll be set up with this nice format. So we do 0 to 4, and then we put our function in here, which was, now I already had it in y1, so just to be lazy, I'm going to do vars, y vars, function y1, and I'm going to integrate with respect to x, and you'll see in a second that this is going to be really important, and then you hit enter, and then you get your 10.6667, okay? So the idea is just being able to set it up and get the correct integral, and then we can use the calculator to find the answer. All right, so then coming back to this, now suppose we do another example, which is find the area bounded by y equals x squared minus 4, y equal to 0, which of course is your x-axis, and x equal to 4. Now in that one, notice that when I'm giving you the x equal to 4, I'm giving you b, okay? That I'm giving you the upper bound, but notice I didn't give you the lower bound. So you're going to have to figure out what the a is. So, and since a is where you are on the x-axis, you can solve for it by letting y equal 0 and solving for your x-intercept. Now, even though you got negative 2 and 2, since you're trying to find the area bounded by these curves, you want to make sure you go, well, that point would have to be my x equal to 2. So when you set up your interval, what you're basically going to do is you're going to do your boundaries as 2 and 4, and then underneath of the curve to the x-axis. So we would do the integral from 2 to 4 of x squared minus 4 dx. Now I'll show you this one. Now you get the same answer, that's just coincidental. I just want to really quickly show you on the calculator though, if your calculator is one of the older ones, for those of you that don't have the nice pretty print on it. First thing, I'm going to turn myself to classic print so that if you have one of the older calculators, you can see how the function int works for the old calculators. Now when I go to math and 9, I have this. I don't have the little pretty little integral symbol. So I have to remember that what I'm going to do is I'm going to put in my function. So I'm actually just going to type it in this time because I don't have it in my y equals. So x squared minus 4. I'm going to put a comma and say, hey, my variable is x. Just come back here. And then you got to give it the bounds. So it's going from 2 up to 4. And then close your parentheses and hit enter, and then it gives me that 32/3, which is 10.6667. Okay, so that's just to kind of show you how that looks if you have one of the older calculators. Now, I like the pretty print, so I'm going to put myself back in that because I find that to be a little easier, and you do whatever your calculator is going to do. All right, so those are pretty straightforward, reviewing what we'd already done. Now let's go to the new part, which is what if instead of being bounded by the x-axis in the curve, we're now bounded by the y-axis in the curve. And the first thing you're going to see in my little area calculation, and again, this is also assuming that this function is always on the positive side of the y-axis, that the function is not a function of x anymore, but it is a function of y, and we have changed this to be going with respect to y. Now let's talk a little bit about the reason why. So let's take a look at this example down here. So I want to find the area bounded by y equal to 4, which is this horizontal line, the parabola y equals x squared plus 2, and the y-axis. Now, there's actually two kind of ways that we can do this problem. One way is to keep with the vertical elements, keep having our representative rectangles go in the vertical direction. So we're still looking at a width of dx. But then when we go to calculate our height, realize that our height is now kind of the difference between the y equals 4 and the curve y equals x squared plus 2. So kind of just showing you a little bit of preview of using the vertical elements, using the vertical rectangles. I could go from a low boundary of 0. I'm going to have to calculate my b, because I need to find that intersection point. So I'll do that over, let's just stick it right here. So I would have y equal to x squared plus 2, and I'm going to set that equal to 4 to calculate this intersection point. That's going to give me x squared equals 2, x equals plus or minus square root of 2, so this must be square root of 2. So I'm going to do from 0 to square root of 2. And then I'm going to take my top function, 4, and subtract the bottom function, x squared plus 2, because I'm looking for the area that is the difference. It's kind of like taking the area under 4, which is nothing more than a rectangle, and subtracting off the area between the curve and the x-axis, which is here. And when I do that subtraction, the rectangle minus the red part, I end up with the little blue shaded region. And of course I have to finish this out with a dx. Okay, and then we could put this in our calculator and calculate it. But instead of that, what we want to recognize is this is actually a little easier to do by doing the horizontal rectangles instead of vertical rectangles, because it's pretty much the area between the curve and the y-axis. Okay, so now we're going to kind of think about our rectangles as going this way in the problem. So as soon as my rectangles are horizontal, then the width of the rectangle is going to be dy, and then the height of the rectangle, I need to find the x, but I need to find the x as a function of y. In other words, I'm going to plug in the y value to find the x value that's going to give me the height of the rectangle that's going horizontally. And that's why we're making a change in our integration. Now our rectangles that we're summing up, we're going to be summing up with respect to y instead of summing up with respect to x. And then our low bound is going to be here. This is going to be our lower limit. And then this is going to be my upper limit. All right, so let's take a look and see how this problem works going to the y-axis. So instead of this, what we're going to do is we're going to come down here and use the y-axis formula. So we know that our boundary curves, the first boundary, the top boundary curve is 4. Now I need to find the bottom boundary curve, which is really nothing more than f of 0. When you basically are like, hey, here's my y equals x squared, I want to know what the y is when x equals 0. And when x equals 0, that's really easy. You get y equal to 2. So I have a lower boundary of 2 and an upper limit of y equal to 4. Okay. Notice my bounds are now on the y-axis because we're going to be going from rectangles starting at 2 going up to 4, doing horizontal elements. And then the next thing that you have to do after you get your boundaries is what you want to do, is you need to then switch your function, because your height of your rectangle is the x value. And so you have to get the x value as a function of y, which is really nothing more than take the function that you have. Right now we have y as a function of x. Just solve for x so that you can get it as a function of y. Now when I solve this over, I do have the plus or minus, but remember we're in quadrant 1. We want the part of the piece that's on the positive side, so we're going to choose the positive. So now our integral is the integral from 2 to 4 square root of 4 y minus 2 dy. So it's a difference in looking at it because we're looking at it as horizontal rectangles instead of vertical rectangles. Now when I go to do this one on my calculator, the calculator is perfectly fine with whatever variable we want to put in there. So basically when I go to my math and I choose number 9 and I'm doing my integral, I'm going to put in my 2, I'm going to put in the 4, and here I'm going to go ahead and put in the function as a function of y. The calculator is okay with that. As long as you tell it what you're taking, differentiate or integrating with respect to, we're perfectly fine with it. So we're just going to go alpha and y minus 2, and then put our integrate with respect to y, so we put our y down here. It is perfectly fine with that. Of course, don't add little extra things like my calculator does. And then I'll hit enter, and it will give me the approximation. And then just to verify, that is for square root of 2 divided by 3, which is the answer that I had over here on the sheet. So the calculator doesn't really care whether you're differentiating with respect to x or with respect to y. Now that's partly why I showed you how to do this on the home screen, because your calculator does not graph x as a function of y. So it doesn't work as well when you go over here to the graphing portion to try to find that. So what you really want to do is you want to make sure that you're doing this on the home screen using the function int command. All right, so now that we have the idea of kind of what's going on here, let's take a look at another example. So I want to find the first quadrant area bounded by the arctangent function, inverse tangent, pi over 4, and x equal to 0. So x equal to 0 is code for y-axis, and if you take a look at the picture, you can clearly see that I'm really bounded between the function and the y-axis. And as soon as I see that, I start thinking to myself, I think that having a horizontal rectangle with a dy would make more sense in this problem than doing a subtraction of the top minus the bottom curve for the x. And so that way, we're going to go ahead and show you how to set it up. We are doing the same thing. I need to find this intersection point and that intersection point to get my lower limit and my upper limit. And if you know anything about inverse tangent, you know that this is going to be y equal to 0. And you know the top one, of course, is y equal to pi over 4, because they gave it to you. So when I go to set up this integral, my integral is going to go 0 to pi over 4. But then remember, right now I have y equals arctangent of x. We have to solve that to get my x, my height, as a function of y. So what is the inverse of arctangent? Tangent. So I simply switch my perspective to get my x equals equation. And then I'm calculating my area by doing 0 to pi over 4, tangent of y, dy. And again, the idea is that you're going to have more algebra ways to find this once we learn our shortcut. But since we're just practicing our setup here, we can come right back into math, choose function int, tell the calculator 0 to pi over 4. Whoops. And we're going to do tangent of y, alpha y, and with respect to y. And then again, just beating a dead horse, you do want to make sure before you do anything, since I have a truth function, that my mode needs to be in radian. And so I'm going to change it because I obviously teach more classes than calculus, so I've been switching back and forth. So I make sure I'm in radian mode, and then I can hit enter, and it will give me the decimal approximation. And then again, just to verify, 0.5 times my natural log of 2 gives me the same answer. Okay, so differentiating with respect to x, differentiating with respect to y, integrating with respect to x, integrating with respect to y. It should not matter. It's just kind of a change in perspective in terms of these area problems that we're going to be looking at. All right, so now let's go to the area between two curves, okay, where this gets to be a little bit more fun. So we want a general approach to finding area, okay? Now, if we're unsure of, and this is just kind of a universal formula for finding area, if you're unsure which function is on top when you are doing this, then what you can do is you can do the absolute value, because if you did bottom minus top, you would just have a negative area. So if you do absolute value, that would just make it positive. And so it'll work out and everything will be fine. The one comment about finding the area between two curves is we are essentially trying to look for, if the curves come here and here, the area between the two curves is this area right here that they're going to be looking at, okay? And typically it'll be fairly obvious what enclosed region you're going to be looking at, all right? Now, notice that I'm talking about the area between. It definitely, like in this case, you will start to make some decisions about, is it better to go with respect to x and do vertical rectangles, which this would be an example where I would probably do the vertical rectangle and do the width as dx. But there will be other cases where it will be more appropriate to do it as a function of y and to do a horizontal rectangle. So it might be something where you're more along these lines, and then so your top and your bottom kind of go this way, and it might make more sense in the problem to do a horizontal rectangle instead of a vertical rectangle. All right, so here's an example. Now in this one, we're given e to the x, which is here, x squared minus 1, and then they gave me some boundary curves. So I want to find the area between these two. Now the subtraction is still going to work, even though you might be worried a little bit about the fact that this area down here is below. But if you always do top minus bottom, I'm going to do the e to the x minus, don't forget your parentheses, x squared minus 1, that if I do the top minus the bottom, then this, which will be a negative signed definite integral, becomes positive when I am integrating, because I am subtracting the negative, which becomes positive again. So it will actually end up being the area between. So we're okay with this. In looking at this, you kind of make a decision, and I definitely, since your low bound is an x equals, your high bound is an x equals, that I would do this as a vertical rectangle, kind of draw in your representative rectangle, and I label that as dx to remind myself that this is a with respect to x problem. So I add my dx after I have subtracted, and then we're going to basically do our lower bound is -1 and our upper bound is 1. So this example is an example of where it's definitely better to go ahead and do the vertical relationship instead of the horizontal. Why is the horizontal bad? Because if I was going through the horizontal trying to go this way, you don't actually have between two curves. You see how it has a vertical line, top curve, bottom curve. If we had a situation where we had a horizontal line, a left curve, and a right curve, then that would make more sense to go horizontal. So you kind of have to visualize in your mind which would be better. All right, finishing out this example. Okay, and I'm going to leave this for you to go ahead and verify. Here's the integration. Here's the actual answer. I'm going to leave you to verify that with the calculator for your own practice. I want to come down and take a look at example 6 now. I want to find the area of the region enclosed by x equals y squared minus 2. Okay, so that's this curve right here. And this one would be considered the quote-unquote bottom curve because it's the one that is most to the left. And then you have your y equals x. Okay, and notice they're using subscripts just to designate you have two functions. They don't always do that. They might just say x equals y squared minus 2 and x equals y. And you realize you have two different functions. Now notice that in this version, when I'm trying to find this area, I'm not really going to try to find this area between by doing a vertical, because right here is where the problem is. If I were to try to think of this as vertical rectangles, from this part all the way over to here, vertical rectangles will be great because I'm taking top curve minus the bottom curve. But then when I hit here, I no longer have top curve minus bottom. The problem is that I have something that's not a function of x, and that's why this is not a great problem to do with the vertical rectangles. So instead, we recognize that if I were to use the horizontal rectangles, in the horizontal rectangles from the beginning, the bottom of the section, this is going to be my lower limit, to the top of the section of the shaded area, so up here is going to be my upper limit, that for that graph I have a top curve, which is the one to the right, and then I have a bottom curve, which is the one to the left. And so it would make more sense to do this as a horizontal rectangle with dy as its width and the height as an x equals. Okay? Now we basically need to find several things here. I've got to find my lower limit and my upper limit, which is the intersection of the two curves. And that should be fairly straightforward, a little bit of algebra 2, where we are simply going to set the x's equal to each other and solve the system for our solutions. And we get y equals 2 and y equals -1. So this lower limit is y equals -1, and this upper limit is y equal to 2. So we're going to run the integral. We'll start setting it up here from -1 to 2 of your top curve. Now remember, because I'm doing this with respect to y, I have to make sure that my functions are x equals functions of y, and an x equals another function. They have to be written as x equals a function of y. Now they were very nice to you. They gave them to you in x equals form, so we don't really have to do a lot of work. And the top curve, the one that's most to the right, is the y equals x, or x equals y, minus the bottom curve, which is the x equals y squared minus 2. Y squared minus 2 dy. So that's our setup for the area between these two curves. And then I will leave for you, here it is again, showing that little definite integral that I have up there, to verify that your answer is 9/2 using your calculator. All right, let's take a look at example 7. Now I want to find the area enclosed by the curves y equals x squared, y equals x plus 6, x equals 0, and x equals 5. Now what's interesting about this one is that the one curve that's on the top switches to being on the bottom in the middle of the curve. So you can't do, it's kind of like the above the x-axis, below the x-axis that we were talking about before. I can't actually do this as one integral. I'm going to have to split it up where they intersect so that I can do this top minus bottom for the first integral from a to b, and then I'm going to switch, and the bottom becomes the top, and so I'm going to do this one as the top minus the bottom here. So you have to make sure you kind of pay attention. This is why you're sketching in all of these to find the area between the two curves. All right, so the intersection point, again, we're going to solve, set the two equations equal to each other, y equals x squared, y equals x plus 5. Oops, that should be x plus 6 right there. And then so we're going to solve. I'm going to go ahead and, very nicely, they made the typo, but then they're correct here, because this does end up being minus 6, minus 3 plus 2, and so on. And so we get 3 or -2. Now, the -2 intersection is that one, which is not my interest in this problem. My interest in this problem is only the x equals 0, the y-axis, and so on. Okay? And so on this, we're going to do the top minus the bottom. Notice the top minus the bottom from 0 to 3, which would be the b value that we found here, b equal to 3. Top's the line, bottom's the parabola. And then I want to switch. I want the parabola on the top and the line on the bottom for the next subtraction. And I'm going to leave you to verify that this is the correct answer using your calculator. Now you could also set this up as to be horizontal as well. I'm going to go ahead and, well, no, I'm not. Now, why would I not want to do this as the horizontal? First off, the lines that we were intersecting are vertical lines. There are no horizontal lines that I am using for my low bound and my upper bound. And so I kind of have a problem. I could probably go, yeah, it would have to be, you'd have to break it up too much because you would have to do the area between this curve and the y-axis, then the subtraction of this curve and that curve, and then you would have to switch and do the subtraction of this curve. So it would end up being 3 integrals if I tried to do it with the horizontal rectangle, so that is not a good idea in this case. So do you see how you have to kind of recognize what would be the best way to do this problem? You're still stuck with 2 integrals, but the best way here is to have vertical rectangles as we are doing this, which means you are differentiating with respect to x. All right, let's take a look. I think I have one more example on here in this, or actually, no, I don't. We get to some practice problems. So what I want you to do for these practice problems is I want you to sketch, okay? So that's kind of probably the very first thing you should do in all of these things. And I want you to sketch, decide whether you want to integrate with respect to x or y. Show me a representative rectangle on the problem. Just designate whether you're going to do the vertical with the dx or you're going to do the horizontal with the dy. Then I want you to write the definite integral that is going to be used to find the area between the curves. And then I just want you to use your calculator to approximate the area. And then that will finish up our little area by integration notes that we have for today.